Welcome to AP Chemistry at Heimendiga High School. I'm BBrown, and today we'll be looking at the middle 4 sections of Chapter 6. Now, we already talked about how classical physics had treated light like waves and particles as if, or matter as if they were particles. And we already looked at how we couldn't explain all the properties of light by just treating it like a wave. In some respects, there are certain situations where light behaves more like a particle. Well, once that had become an idea, it wasn't long before scientists, and in particular Louis de Broglie, had basically looked at it from the other point of view. And they said, well, if light can be treated like a particle sometimes, maybe particles can be treated like waves. So he was looking at the wave-like properties of particles, and using Planck's constant, he was able to come up with an equation that looked like this. And he was demonstrating the relationship between the mass of a particle and its wavelength. So h is Planck's constant, m would be mass, and v would be the velocity, and mv would be the momentum then of the particle. So it was really looking at the relationship between momentum of moving objects and their wavelength. Now, this is an equation that honestly we could do calculations with, but what I want you to understand more than anything else is the implications of this. So we're not really on the test going to be solving this equation ever. You just need to understand that for the first time, somebody had treated a particle as if it was acting like a wave. And the significance of this equation isn't when we have everyday larger objects, but it would be true that the smaller the object becomes, the more important its wave-like property is. And that's really the biggest thing to understand about this. Now, related to this idea is Heisenberg's uncertainty principle, which you may have heard about last year in pre-AP chemistry. And what Heisenberg was trying to do was to show that you can't precisely both know the position and the momentum, and momentum would be tied to energy of a particle at the same time. Now, at the time that this came out, this was a huge problem in science because scientists, particularly chemists and physicists, were hot on the trail of understanding the electron. And they figured if they could understand the position and the energy of the electron, they would understand chemical and physical properties much better. So they were really closely looking at knowing what exactly Heisenberg said they couldn't both know with a great degree of certainty. And for a number of years, scientists wasted energy trying to prove Heisenberg wrong. The problem is Heisenberg wasn't wrong. And it is a fact that the more precisely you know the position of an object, the less precisely you know its momentum or energy. So his fundamental idea really set scientists on their heels because they were looking for these two precise things. They figured they needed to know the position and the energy of electron. And they wasted a ton of time trying to prove Heisenberg wrong, but he wasn't. And what you really need to understand here is the more precisely we know position, the less precisely we know energy. The more precisely we know energy slash momentum, the less precisely we know position. And like de Broglie's equation, this is a calculation that we could do, but really it's a conceptual idea you understand or need to understand more than quantitatively being able to calculate this thing. So this is not something we're going to practice in homework. It's not something that's going to be on the test, but it is a conceptual idea you need to understand for the test. And the way it works is, in many cases, our uncertainty about where an electron is so great when we know its position as precisely as we can, or I should say, when we know its energy as precisely as we can't even say the electron's even inside the atom anymore. So the positional uncertainty becomes so great when we know the energy slash momentum too precisely. Now, how did scientists get around? Because we really wanted to know precise information about both the position and the energy of the electron. And like I said, scientists wasted a ton of time trying to get around Heisenberg's uncertainty principle until finally along came a scientist by the name of Erwin Schrodinger. And Erwin Schrodinger basically was the first person to think outside the box and realize, well, wait a second. What we really would like to know is more precise information about the energy of the electron. And if we're going to get more precise information about the energy of electron, we're going to be stuck having uncertainty about position. And he basically said, well, that's perfectly fine. I mean, think about it. If I want to mail you a letter, I don't need to know where you're at every second of the day. I just need to know where your house is, where you're at a decent chunk of the day. So he got around the uncertainty principle by really realizing that we didn't need to know precise information about both. And he developed what are known as the wave equations. So he came up with a mathematical treatment into which both the wave and particle nature of matter could be incorporated. So he was looking at a situation where he was incorporating both particle and wave-like properties of small particles like electrons. Because as a very small particle, its wave-like properties become very significant. And what was really born here was the birth of what is now known as quantum mechanics, a different way of looking at the electron. Now, the square of his wave equation, which is given by this symbol right here, gives the probability of finding an electron in a certain location. So basically, it's showing what is the likelihood that the electron is going to be at this precise location right here. And it's often known as the probability density or electron density. Now, if you look at this diagram, this may look familiar to you from pre-AP chemistry. We refer to this type of thing as the electron cloud, and it's really another way of expressing the probability density. So when you look at this picture, you can see, well, most of its time it looks like the electron lives in here, and as we're getting farther away from that center, it's less and less likely that the electron is going to be found there. Now, a region of high electron density then would be an area with a very high probability of finding electron. And his wave function, therefore, really gives us a way to look at the shape of where the electron lives, which we call the electron's orbital. So based on this picture, you can see that this electron appears, because we're looking at an image of where one electron is living, it looks like this electron appears to live in a spherical shaped orbital or spherical region. So solving for the wave equation gives us a set of wave functions or orbitals and their corresponding energies. So what he was able to do is to look at general location and specific energy information. Now, each orbital actually describes a 3D region of space where the electron is found 90% of the time. And any specific orbital, basically a little apartment where an electron lives, can be described by what are called 3 quantum numbers. Now, while the AP test no longer requires you to be able to write and understand quantum numbers, because really quantum numbers are related to information you learned in pre-AP chemistry, but we're actually giving them specific numbers so we could come up with an address of the electron. Now, in the AP test, we no longer have to be able to do that, but the concepts related to this are still concepts that we do have to understand. So we often use the term quantum number, and then we don't talk about numbers. Well, that's because there really are numbers associated with them, and we're just not going to get into what those particular numbers are in AP chemistry anymore. Now, these 3 quantum numbers need to be used to describe an orbital. And the quantum numbers we're talking about here would be the principal quantum number, and that's the only one we're really going to call quite often a quantum number, and it's the only one we give a number value to. Now, the symbol n, which you should look familiar to you from pre-AP chemistry, because if you got into electron configurations, n is the energy level. So the one quantum number we will talk about is the principal quantum number, the first quantum number, and that is related to the energy level, and that we will give an actual number value to. Now, the second piece of quantum information or quantum number is really related to the sublevels. So we have energy levels, and then within a level we have energy sublevels. And these are related to the shape that the orbital is. So the shape of the apartment, it's an actual 3D region of space. SPDF, those should look familiar from last year as well. And then finally, the third bit of quantum information we need to describe a location of electron is the orientation of the orbital, because you can have different p apartments, different orientations of a p orbital, and the same with a d and the same with an f. So really the orientation is looking at which orbital on the sublevel that electron is living in. So between level, sublevel, and the orientation, we can talk about a location of an electron. So those are the 3 things we really need to describe to talk about which orbit an electron is living in. Now, the principal quantum number n then describes the energy level on which the orbital resides. And it deals with the distance from the nucleus and general energy. So to really get to specific energy, we need to get into sublevel information. So it's general energy and a specific distance from the electron. Now, Energy levels would start with the first and they're numbered up from there. So the first energy level, second, third, fourth, fifth, and technically that goes on to infinity. But when we look at the few electrons we actually have in a typical atom, even a very large atom, we don't really need that many energy levels to describe those electrons. And a bizarre idea about energy levels is the higher energy you get, the closer and closer and closer they get to each other. And eventually, this deals with the idea of limits from math class. Add any more energy, and you're basically going to be out of the atom. So there is a finite limit to how many real energy levels we worry about. But for the most part, we're talking about 7 energy levels because that's all we need to talk about the number of electrons that are even in our largest atom. And it is important to remember that the higher the energy level, the larger the atom, and the farther the electron is from the nucleus. So an electron in the 7th energy level is farther from the nucleus than an electron in the 1st energy level. And that's an important concept because remember, our nucleus is positive, our electrons are negative. Coulomb's law deals with the force and the energy of those attractions. And the farther you are from the nucleus, the less strongly the nucleus holds on to you through Coulomb's law. Coulomb's law threads through all of the discussion related to atoms and electrons. Now, the second bit of quantum information we're going to look at deals with the sublevel or shape. So we're talking about shapes, we're talking about specific sublevels. Each energy level contains sublevels. And this is really where Bohr got it wrong, because when you have one electron, it would be true that all of the sublevels are at the same energy. So really, n was all that was important. But when we get more than one electron, the sublevels split off from each other. That's something we'll get into more later. Now, the number of sublevels on a level is related to the energy level you're on. So it actually equals the energy level. So on the first energy level, we only have one sublevel. On the second energy level, we would have 2. On the third, we would have 3, and so forth. So if you know what energy level you're looking at, you know how many sublevels potentially exist. So once again, we get in the idea that, yes, there are technically an infinite number of potential sublevels, but the reality is we only need to worry about 4 different kinds of sublevels. Now, each sublevel contains orbitals, and those are actual apartments, regions of space where an electron lives. And remember, an orbital is a place where that electron is going to be found 90% of its time. And one of the fundamental ideas you should understand, and hopefully you grasp this from pre-AP chemistry, is that the center of every orbital is basically the nucleus. And therefore, you have electrons in different orbitals visiting other orbitals all of the time. They just don't live in that particular region of space 90% of their lives. They live in their orbital and region of space 90% of the time. Now, each orbital can hold up to 2 electrons. So every apartment, region of space, orbital that electrons can live in can hold up to 2 electrons. And the total number of orbitals on an energy level is actually related to the energy level. So remember, sublevel and the total number of orbitals on a level are all related to n. In this case, it's n squared. So on the first energy level, 1 squared, we only have 1 orbital and that's it. But when you get to the second energy level, 2 squared is 4. So we're going to have a total of 4 orbitals living on that second level. And remember, since it's a second level, it has 2 sublevels. And there'll be a total of 4 orbitals on those 2 sublevels. And each sublevel has a different shape. And that corresponds to the SPDFs that you may remember from last year. So these are actually the shapes of the orbitals. So S, P, D, and F are our different shaped sublevels, or the different shapes of orbitals we have. Now, the third bit of quantum information is orientation. Each shape of an orbital has a different number of orientations in which they can exist on a sublevel. Now, the first shape, S, is our spherical shape, which is probably where the symbol S comes from. If you picture a sphere like a basketball and you spin it around its center point, it doesn't occupy a new region of space. So there's no way we can, without moving the basketball to a new location, actually occupy a different region of space. And that's why S orbitals only have one orientation. Because remember, the center of our orbital is the nucleus, and we can't move away from that nucleus. The nucleus is where the nucleus is. So when we rotate our S orbital, we're always in the same region of space because it's a spherical shape. So there's only one S orbital on a sublevel, or I should say 1s orbital in the s sublevel. There's only one orientation. But when we get to p's, we now have 3 different orientations. And we look at the shapes in a second, it'll start to make more sense when you see, oh, I can rotate that kind of shape and end up in a new region of space. So there's 3 different p apartments on the p sublevel. There's 5 different Ds and there's 7 different Fs. So it's a pattern here, 1, 3, 5, 7. So the S sublevel just has 1 apartment. The P sublevel always has 3 potential apartments for electrons. Ds have 5 and Fs have 7. So between those 3 bits of quantum information, we can describe which particular orbital an electron is in. Now, there's 2 other terms you need to be familiar with for the AP test, and these terms are used interchangeably. I tend to use level and sublevel more often because that's what I'm familiar with, and so does your book. But you do need to understand that orbitals with the same value of n form what are called an electron shell. So on an energy level, or an electron shell, we have orbitals. So basically on the third n, so on the third energy level, we have a wide variety of orbitals that live on that energy level that make up what we call the electron shell. Now, different orbital types within a shell are called subshells. So on the third energy level, we have S's, P's, and D's as sublevels and shapes. So that means we actually have 3 subshells within our third level electron shell. So, and those are terms you just need to be familiar with. So electron shell is referring to all of the orbitals within a level, and a subshell is referring to basically a particular shape within that level. Now each level or I should say for s orbitals, every single energy level has an s or spherical shape sublevel. So the first, the second, the third, and so on all have an s sublevel. And there's only one orientation of the s, which I already talked about. So on the s sublevel, you can only hold 2 electrons, and then that sublevel is full. And fundamentally, and this is the pictures you see on the left here, as n is increasing, our orbital is getting larger. So the 1s region of space is smaller than the 2s region of space. So the electrons that live in the 2s orbital are on average farther away from the nucleus than the 1s orbitals are. Once again, that means the nucleus has a weaker hold on them because they're farther away, and Coulomb's law says distance kills attractive forces. And remember, the electrons that live in our 1s orbital visit the 2s orbital all the time because that 1s orbital is inside the 2s orbital. It's just the electrons in here spend 90% of their lives in this region of space, and then every once in a while they're outside of it. But our 2s electrons live in this region of space 90% of their lives. So they visit the 1s apartment all the time. They're just not there 90% of their lives. And that's the s orbital. Now the next type of orbital is the p orbital. Now the second energy level and above has a p sublevel. So remember, s's are on every energy level, but p's are only on the second and above. There are always 3 orientations of p, and you can see why here. Now this is over here our electron density or electron cloud type drawing. It's a little bit easier to see it in the pictures we have in these 3 positions. So picture a dumbbell, and it is sitting along the z-axis. Well, if I spin it just a little bit and get it on the x-axis, I'm in a new region of space. If I spin it 90 degrees again, I'm along the y-axis, and once again, I'm in a new region of space. So there are 3 different orientations, or 3 different p apartments on every energy level that has p. So the second and above always have 3p orbitals. And remember, they have 2 lobes, but that's still just one orbital. This is a region of space where up to 2 electrons can live. So a p sublevel can hold a total of 6 electrons. So if every p orbital is filled with 2, that's a total of 6 electrons to fill that whole sublevel. And so remember, first, if this is like an apartment building, the floors are energy levels. The first floor has an S apartment, and that's it. When we go to the second floor, now we have an S apartment and we have 3 P apartments. When we go to the third floor, not only do we have our S, and it's a little bit larger than the S apartment down a floor, and we have our 3 Ps, and once again, they're a little bit bigger than the Ps down a floor. But when we get to the third energy level, we have a new shaped orbital, which is the D orbital. So the third energy level and above have a D sublevel. And there are always 5 orientations of Ds. And remember, at 2 electrons apiece, that means it would take a total of 10 electrons to fill our whole D sublevel on the third floor. Fourth floor and above, we also have an F sublevel. So 4, 5, and 6 and beyond, we have F sublevels. And now we're starting to get pretty funky looking orbital regions down here. So it's a little harder to see that these are unique regions of space. But there are a total of 7 orientations of an F. So there's 7 F apartments that can hold electrons. And at 2 electrons apiece, that'd take a total of 14 electrons to fill the whole F sublevel on the 4th or the 5th energy level. Now, for a 1 electron atom like hydrogen, orbitals on an energy level all have the same energy. So notice we've got our 1s apartment here. And then on the second floor, we have our 2s and our 3 2p apartments. So there's 4 blocks there. So we have a total of 4 orbitals on that second energy level. But notice they're all at the exact same energy. Now the term for that is degenerate. So if we only have 1 electron, then the energy sublevels are all at the same energy on an energy level, and therefore they are degenerate, which means they're all at the same energy. Now, as we add electrons into an atom, the electrons, remember, are all negatively charged, so they start to repel each other. And what happens is our sublevels are no longer degenerate. They split into different energy amounts. And you'll notice on each of our apartment floors here, the second, the third, and the fourth, the S apartment is always lower in energy than the P's. And that's something that gets repeated on every single floor. And that's why the view of the atom was a little bit more complicated than Bohr thought it was. His mathematics were great for 1 electron. But once we got 1 electron, or once we picked up a second electron, the mathematics started to go away. And that's because it wasn't as simple as looking at energy levels. The true energy is really what sublevel you're on. So they are no longer degenerate because of the electron-electronic repulsion that exists. So in a many electron atom, orbitals on the same energy level are no longer degenerate. They're no longer at the same energy. Now, the last bit of quantum information is called the spin quantum number. And the symbol is shown there, but you don't need to know the symbol. Think of it as spin. This is how we tell apart 2 electrons in the same orbital. Because one of the principles we're going to get into is that no 2 electrons can have the exact same quantum address. So there has to be something that differentiates the 2 electrons that are in one orbital, and that is the spin quantum number. In the 1920s, it was discovered that 2 electrons in the same orbital do not have exactly the same energy, which makes sense because when we put the second electron in there, they're going to repel. So that second electron should be higher in energy than that first electron in. But we really only have 2 positions, that lower energy the first one in and that higher energy the second one in. And at that point, we can't fit any more electrons. Now, the spin of the electrons describes basically its magnetic field, which affects its energy. When we have opposite magnetic fields, they can attract. But if we have any other magnetic field, they're going to repel one or the other, and it's no longer going to stay in that same region of space. So this really led to the 4th quantum number, and that's the spin quantum number, m sub s. Now, this is what I'm going to show you the numbers, but once again, don't get hung up by the numbers, because what we're really going to do is use up and down arrows to differentiate between the different types of spins. So the spin quantum number really only has 2 values, the positive 1/2 value and the negative 1/2 value. And that allows us to differentiate between the 2 electrons inside the atom, the one at lower energy and are inside the orbital, the lower energy electron, which is always our first electron in the orbital, and then the slightly higher electron energy. But they are very, very close in energy, just not quite at the same energy value. So no 2 electrons in the same atom can have the same exact energy and the same 4 bits of quantum information about them. And that's what's known as the Pauli exclusion principle. Now, if we got into quantum numbers, that would physically mean if we wrote the 4 quantum numbers for a specific electron, no other electron in that atom can have the exact same 4 set. They can share 1, 2, or 3 of those 4 bits of information, but not all 4. Therefore, no 2 electrons in the same atom can have the same set of quantum information. And that finishes our second set of notes on the chapter.